Hello students, welcome to the second video of structure and bonding lesson. Without any delaying, let's go to the lesson. Okay. Now in last lesson, we discussed what is a bond and what are the types of bonds and what else? What are the types of bonds and sigma bonds, pi bonds, and we compare the strengths of them, and yeah, we've done with it. So today we will discuss how to prepare the atoms for bonding. Now, you should before marrying, okay, you should prepare yourself to marry, right? Like you should be stable. You should prepare yourself. It's the same thing with atoms, okay? Now, in this video, we are going to see how we prepare the atoms for bonding. Preparing of atoms. Atoms for bonding. For the topic, preparation of atoms for bonding. So when you want to write down something while I'm explaining, you can pause the video and you can continue write. Okay. Now, preparation of atoms for bonding. How do we prepare atoms for bonding? Now, the first point is preparation of atoms for bonding means excitation. Okay? We use the term excitation. Excitation of atoms. Okay. Let's discuss about this in detail. Before that, just remember, preparing an atom for bonding means we are exciting that atom. Okay, just remember that term. Now, my excitation of atoms means we are increasing its valency. Okay, you know that valency. You know valency from first unit. We are increasing the valency so that, let's say, an atom usually forms only 3 bonds. An atom usually forms only 3 bonds. So, like with its electronic configuration, it usually forms only 3 bonds, but by excitation it can form multiple bonds. Okay, so basically, valence excitation of atoms means we are increasing the valence. Now, to understand this part, let's go into the examples. Okay, let's go into the examples. Now, let's say an atom A. This configuration is 1:2, 2:2, 2p2. So how are the orbital arrangement? How are the electrons filled in the orbitals? 1 and 2. The electron is filled like this in the orbitals. Okay? You call this ground state. Ground state of the atom. Then what happens in excitation is now the electrons now excitation means electrons from this orbital is sent to an empty orbital. Okay, electrons from a completely filled orbital is sent to an empty orbital so that the number of lone electrons are maximized. That's what excitation means. An electron from a completely filled orbital of the same energy level. Remember how an electron from a completely filled orbital within the same energy level is transferred to an empty orbital. Write down the definition by an electron from a completely filled orbital of the same energy level is transferred. Now this guy is transferred to this empty orbital of the same energy level. Now you can't transfer this electron to 2sp, this one, this orbital, okay? You cannot transfer like that. You can transfer a completely filled orbital of the same energy level to an empty orbital of the same energy level. That's what is called excitation moment. Now, see, from 2 lone electrons, it has gone to 4 lone electrons. What does that mean? From making 2 bonds, now he can make 4 bonds. From at the beginning, he was supposed to make 2 bonds because he has only 2 lone pair electrons. At the end, after excitation, he has 4 lone electrons so that he can make 4 bonds. So, to form a covalent bond, you want an orbital with 1 electron. Right? Now you have 4 orbitals with 4 lone electrons. So you can make 4 bonds, 4 covalent bonds. Okay. Now let's go into the examples of the tube. Okay. Go into the examples of the tube. So, okay, let's go into the examples of the tube. Okay, now carbon. The electronic configuration is 1s2, 2s2, 2p3. The ground state, if we draw this, we will get like this. So excited state. So after excitation, the state is called the excited state. So at that state, I told you, electrons of another energy level cannot be transferred to an empty orbital of another energy level, okay? So, as my definition, I transfer the electron of a completely filled orbital to an empty orbital of the same energy level. Okay, from here to here. Now, in the same way, if we take boron, 1s2, 2s2, 2p1, ground state, like this, like this, like this. Excited state. See, I transferred an electron from a completely filled orbital to an empty orbital of the same energy level. Okay, you can pause the video and write the examples down. What about phosphorus? Okay, phosphorus is a special point. For now, let's take this down. Okay, phosphorus is a special. Pause the video and take this note down. Okay. Now phosphorus. Phosphorus, what is the electronic configuration? 1s2, 2s2, 2p6, 3s2, 3p3. This is the example. This is the electronic configuration of phosphorus. Ground state. Without drawing these, because you know, in bond formation, only the valence orbitals participate in bond formation, so I'm not going to draw the orbitals of these 4 orbitals which are not going to participate in bond formation, so I'm just directly drawing the orbitals of third energy level. 3s2, 3p3. Excited state. If you are exciting phosphorus, now this is a special point. This is a special point. If we are exciting phosphorus, now this electron is, now what's the definition? What's the requirement to form excitation? What's the requirement for excitation? You must have, it must be the same energy level. You must have an empty orbital and you must have a completely filled orbital. Empty orbital, completely filled orbital. Here we don't see an empty orbital, right? Lamai, we know that in third energy level, it doesn't stop with P. It doesn't stop with S and P. We know that it has 3D energy levels as well. So you can write in this place 3s2, 3p3, 3d, 0. And you draw the 3d orbitals. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. So, where you know that in third energy level there is 3d orbitals and 3d sub energy level. So, where will this electron go? Yeah. The 3d sub energy level. So in the excited state, how you are supposed to write this? Actually, 3s like this, then 3p energy level, and then 3d. Okay, this is 3d energy level. 3s, 3p, 3d. So initially, how many bonds it can form? 3 bonds. After excitation, how many bonds it can form? 5 bonds. That's why we have PCl3 and PCl5. So in PCl3, the bonds of phosphorus are formed at ground state. When the phosphorus is at ground state, 3 chlorine atoms are bonded with the phosphorus. In PCl5, it is in the excited state. Okay? It is in the excited state. So it can form 5 bonds. That's the special point for this part. So there is a question in the next page. We'll discuss that question. Okay. Question number 2. Determine whether the following atoms will undergo excitation or not, and determine valency in the ground state and excited state. So we have sulfur as the first example, first question. What's the electronic configuration of sulfur? 1s2, 2s2, 2p6, 3s2, 3p4. So ground state, and we know that it has 3d 0. At ground state, we are usually drawing these orbitals. So 3s2, 3p4, 1, 2, 3, 4, and 3d 0. So where are these electrons supposed to go? This one will go here, and this one will go here. So in excited state, 1, 2, 3, 4, 5, 6. In excited state, it totally can form 6 bonds. 6 bonds because it has 6 lone electrons. Non-excited state, it can form 2 bonds. 2 bonds. Okay, now this is for the sulfur. What about for chlorine? Next example, chlorine. The electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p5. So ground state will be 3s orbital, 3p orbital, and 3d 0. 3d 0. This electron will go here, this electron here, and this electron here. At the excited state, the orbitals will be arranged like this. 2, 3, and 7 electrons. So 7 bonds can be formed. Chlorine at the excited state, 7 bonds can be formed. Okay. Okay. So what about nitrogen? Next question. You can pause the video and take this down. So nitrogen. Nitrogen, the electronic configuration is 1s2, 2s2, 2p3. So how the orbitals at ground state are there? 2s2, 2p, 1, 2, 3. So what are the requirements to excite? What are the requirements to excite an atom? An empty orbital and a completely filled orbital of the same energy level. Let's say the same second energy level, of the same third energy level. That's what I'm trying to mean by same main energy level. So does this have an orbital that is completely filled of the same energy level? Yes. Does this have an orbital that is not filled of the same energy level? No. So can nitrogen undergo excitation? No. Simply the answer is nitrogen cannot undergo excitation. Nitrogen cannot undergo excitation. Next question. Oxygen. 1s2, 2s2, 2p4. Ground state configuration 2s2, 2p4. 1, 2, 3, 4. Again, what are the requirements to form to excitation? What are the requirements for excitation? An orbital that is completely filled, an orbital that is not filled at the same orbital. What about this one? This doesn't have an empty orbital. So oxygen also cannot undergo excitation. Oxygen also cannot undergo excitation. The next one, we move on to the next one. Silicon. 1s2, 2s2, 2p6, 3s2, 2p2, 2. Isn't it? It is in the same series of carbon silicon, same group. So ground state 3s2, 3p2. Excited state is like this. Okay? Because this electron goes to this orbital. Then we have fluorine. 1s2, 2s2, 2p5. Ground state 2s2, 1, 2, 3, 4, 5. Again, it cannot excite, therefore fluorine also doesn't undergo excitation. Fluorine also doesn't undergo excitation. You can write this point, and the special point I want to tell us here is fluorine under excitation. Fluorine and hydrogen never undergo excitation. Okay. Write this point down. Write this point down. And we will move on to the next section. Let's move on to the next topic. The topic that we are going to discuss is next is type of covalent bonds. Okay. Now before preparation of atoms to bonding, we are going to learn the types of covalent bonds. There are three types of covalent bonds. What are those types of covalent bonds? Non-covalent bond, covalent bond, and dative bonds. Those are the types of covalent bonds. One is non-covalent bonds. Then we have polar covalent. Then we have dative bonds. Okay. Sorry. Is divided into branches. Bonds, polar bonds, dative bonds. Now, what is this? I hope you can see this part clearly. Yeah. What is this non-polar covalent? Non-polar covalent bond is a bond that is formed between two atoms electronegativity of there is no electrons. Okay. Let's do A and B. And electronegativity of atom A is X. Electronegativity of atom B is also X. The electronegativity of atom B is also X. So what is the electronegativity difference? X minus 0. Electronegativity difference is 0. So the bond covalent that is formed with two atoms where the electrical difference between them is 0 is called non-polar covalent bonds. Understood? Bond that is formed between two atoms whose electronegativity is 0 is called non-polar covalent bonds. So which atoms come? How do we do non-polar covalent? An atom forms a bond with another atom of the same element of the element. An atom hydrogen who forms with another atom of the same element hydrogen. An atom who forms a bond with another atom of the same element belongs only to the covalent atom. two. These are the examples. That come on molar covalent bond, hydrogen, fluorine, F2, F2, and so on. So non-covalent means the electronegativity difference between the bond means what? The electronegativity difference between the bond is not non-polar. Polar is electronegativity difference between the bonded atoms is not zero. So take example again. The electronegativity of A is X. Electronegativity of Y is X. Therefore, electronegativity difference. This is different. Find this electronegativity difference is Y minus X. Learn about this category. That's how you write. You score in MCQ. You write these points where explain and so you don't this. Okay. This is electronic of the bonded atoms is less than is than it belongs to the polar category. Between 1 and 2.1 below it can be a polar covalent bond. It can be an ionic bond. Or it can be an ionic bond. It is greater if the difference is greater than 2.1. It is always an ionic bond. So now take this point which we will later detail. For now, this is the electronegativity difference between the bonded atoms is less than 0.8. It belongs to polar covalent. Between 1.8 and 2.1 bond or ionic bond. If it is greater than 2.1, then it is an ionic bond. Write this down. So I have given some examples. Given some examples. You can fill those spaces. You just have to do the structure. Okay. And the next point of polar covalent now. Now, what is a covalent bond? Okay. Now we know what is a polar covalent bond. Now let's take an example HC. Who will have a high electronegativity? Fluorine. Why? It belongs to the halogen series. Group 17. Group 17 elements usually have the highest electronegativity. Okay, so you can just go through the book and get the values from first unit. Polling will show you that the electronegativity around electronegativity is around 0.1. Okay. We'll have a electronegativity. Now in a covalent bond, right? Now how is ionic bond ionic bond? We have to mention this. Ionic bond is not like this, right? Then plus minus. This is the ionic bond. The one who accepts electron, who donates electron is plus, and the one who accepts electron is minus. This is how you know plus and then polar covalent bond electronegativity difference. So also closely similar but not equal. Example, a partial and a partial positive is given to the most less negative and a partial is given to the more negative. This is to give the partial negativity. We call it partial this like this like this like a not a partial negative partial negative. So this is how we know polar bond. If we want to know the positive and negative, this is how we know. The one who has a high negativity get delta negative. Delta negative, this is how we call delta negative. A partial negative and a partial positive charge. Okay. Write this down. So we can write this down. Okay. Then one day this is a pretty part in lesson. Okay, this is pretty lesson. Now we learned about polar negative. All of them are covalent bonds. Covalent bond. Now this is a dative. What are the requirements? First, I'm going to discuss what are the requirements to form a dative bond. The first requirement is we need an atom with base having a pair of electrons. A valence an atom having valence orbital with pair of electrons and having an atom no electrons. No electrons. So say this is the atom A with two electrons. This we can form a dative bond. How both will overlap and both of these electrons are being shared with the other valence of the atom. Both of the electrons are shared with both valence of the other atom. So, what is in a covalent bond? Now this is how we denote. The important point that I try to emphasize here is a dative bond is now this is A two pair of electrons. This is no is being donated. So this is called the donor atom. It's called the donor atom. So this is called the receiving atom. Receiving atom. Receiving atom. So the donor atom is donated as the electron is receiving electron. It is negative charge. So this will be positive and this guy will be negative. After forming a dative bond, this is how we place it. Plus B minus. The one who is donating will have a positive charge and the one who is receiving the will have a negative. Okay. Now after the orbitals are overlapped, can you from whose orbital after you do the after the orbital overlap? Can you which atom of the electrons which you can easily say that one atom donates both of the electrons or both atom get one electrons or the donation of therefore you can differentiate a covalent bond from a normal covalent bond. You can differentiate a bond from a normal covalent bond. Both of them are similar. So in an MCQ you can differentiate a dative bond from normal covalent. True or false? False. Why? Because you cannot differentiate. You cannot differentiate whether it is a dative bond or a covalent. Both look similar. As I want to emphasize, even discuss some examples for dative bond. Now just write this down and write the point which I told you. Okay. Here, write this down. Okay, let's discuss the examples for the dative covalent bonds, which is given. Discuss the examples. Okay, NH4 plus. NH4 plus. Example number one. Example number one. NH4 plus. So, how it is? We have an ammonia in N3. We know the nitrogen, it has a lone pair. It is donated to an H plus. It is donated to plus. So, electron configuration of H is 1s1. So, plus means electronic configuration 1 is 0. So, it is empty. Configuration of nitrogen. What is the electronic configuration of nitrogen? 1 is 2, 2 is 2, 2 is 3. So these hydrogens will form a normal covalent bond, with the nitrogen. So a electron pair will remain in the valence shell of nitrogen. So you have H plus here. So what will happen here now? This lone pair, a pair of electrons, will be donated to this H plus whose orbital is empty. So what will happen is, I told you, one who's donating the electron will get a plus charge. One who's donating the electron will get a plus charge, and one who accepts the electron will get a negative charge. So the nitrogen here will get a plus charge. Plus. The hydrogen plus and minus is 0. So the charge cancel, plus and minus charges cancel. So this is the final structure. The second example H3O plus. H3O plus. Now this is the molecule. We will learn how to draw structures in the next video. For now, we'll just remember this is the H2O, H2O, water molecule and H plus. Water molecule will donate its electron and H plus. Okay. So, what is the electronic configuration of oxygen? Electronic configuration of oxygen 1 is 2 is 2, 2 3, 4. And this hydrogen is in. So these two hydrogens will form bonds with oxygen. This is the bonds with hydrogen. There are two lone electrons. Okay? Two pairs of electrons. One pair is donated to this H plus. The result, the resultant structure is H O H H. So we know that the donating one will get a plus charge and the accepting one will get a minus charge. Plus and minus is cancelled off. It will have plus charge. This is the structure of H3O plus. This is the structure of H3O+. Okay. This is the structure of H3O+. Write this down. Okay, now you might, this is the point here. Carefully, you might think he donated one pair of electrons to H+. So you might think he donated this electron to another H while being only this pair of electrons to another H+. Then that can donate to H at the same time. Is it general? No. People, all of these atoms are people. We made atoms, right? So we don't like to be generous as human beings. We don't like to be too much generous, right? Same thing that he will donate one of electron, but he will not donate the other one. Point here, a molecule or an atom. But how much of electrons using his valence orbital? He will only form one day bond. He will only form one day bond. He has a pair of electrons. Write that point down. Okay? Write that point. Even if a molecule or an atom has multiple pairs of electrons, it can form only one negative. Okay? So this is the maximum limit it can reach. This is the maximum limit it can reach. This method, then try to fill the page. Okay, try to fill the page. So that's the point I want to make. Even though it has lone pair of electrons, now you call, I'll explain the next video. You call this a lone, not just the lone pair of electrons. That's what we say, lone pair of electrons. A lone pair of electrons. A lone pair of electron means donated H+. Okay. Students, it's a long video. I hope you understood something from my talk. Next video we will learn how to draw structures. Okay, that's going to be an interesting part. To draw Lewis structures, and that will carry a huge mark. So clear these topics and watch the next video. Thank you.